Hello, guys. So welcome to our third week of digital design with VHDL. So today we're gonna highlight a new definitions, very useful definitions, basically in expressing Boolean functions. And this is basically what's called minimum term and maximum term, or min term and maximum term, or max term. Okay. So basically, a min term and the maximum term is just a way that we can use to express Boolean functions. Okay, so let's define them first and see how we can use them to expressing Boolean functions. Okay, so basically a min term would be only one at certain combination for the input or the variables of the function. The opposite for the max term. The max term will be zero only at a particular combination of, again, the inputs of a Boolean function. Okay, they are very related, as we will see. Okay, so let's take an example of three variables, x, y, and z. And this is, of course, it can be applied for two variables and for two variables or four variables, whatever variables, number of variables you have. For example, here in this table here, we have three variables, x, y, and z. Okay, let's use our favorite color here. So x, y, and z here, okay, with 8 combinations. Okay, and as we said, the min term will be one only at one particular combination and zero otherwise. Any max term will be zero at a particular combination and zero otherwise, or one otherwise. Okay, the opposite. So here are the 8 combinations, and as we see here, we have 8 minimum term or 8 min terms. Okay, one is called M0, one is called M1, M2, M3, until we have M7. And we have also 8 max terms. We have M0, M capital 0, M capital 1 until M capital 7. Okay? So what is M0? M0 is basically X prime, Y prime, Z prime, or X bar, Y bar, Z bar, or complement, Y complement, Z complement. Okay? So how come M0 will be only one at one term, one combination only, which is basically the first combination here, and zero otherwise. So let's prove that, and I will do that for M0, and it is the same for M1, M2, M3, and so on. Okay, so for M0 here, so let's consider M0 as a function that we're gonna determine at the eighth possible combination of its inputs, which is x, y, z. So when x is 0, y is 0, and z is 0, then x prime will be 1, y prime will be 1, z prime will be 1. So 1 and 1 and 1 will be just 1. Okay, and we said that the min term should be 1 at a particular combination, 0 otherwise. So we're expecting now that for other combinations of x, y, z, we will have 0 for m naught or m0, minimum term 0. So let's do that. X0, then x prime is 1. I'm sorry, x prime is 1. Y is 0, so y prime will be also 1. So far so good. But then z is 1 now, so z prime will be 0. So this will make everything 0. Then we have 0, 1, 0. So x prime is 1, that's good. Y prime is 0 now, and 0 ending with anything will give you 0. I will not continue. Once you find a 0, you don't continue. Okay, it's an AND gate. Then with 0, 1, 1, x prime is 1, that's good. But now y is 1, so y prime is 0, again, don't continue. And here basically x is always 1, so x prime will be 0. So again, x0 ended with anything will give you 0. And as you see, guys, here only 1, 1, and everything else is 0. One term, one combination, which is x bar, y bar, z bar, and everything else is 0. So why we expressed m0 as x bar, y bar, z bar? Okay, ending of these three letters, x bar, y bar, z bar, because basically x bar, y bar, z bar will be only one. This term will be on when x is 0, y is 0, z is 0. That's why we call that combination here, you know, or m naught is corresponding to this combination 0, 0, 0, because at 0, 0, 0, x bar, y bar, z bar will be 1. So it's like you look at the literal, and if it is 0, then you express it with prime, with complement. If it's 1, you express it with just itself. So for example, how about this one? What should be its m? So basically, its m should be x, y, and z here is 0, so z prime. Let's check. Yes, that's correct. Good. We have 8 m's, right? We have 8 minterms in 3 variables, of course, from 0 to 7. Why again we put the subscript as a number? Because basically, this is the number, this is the binary number that you can get out of this term. For example, this one here, this number here, 0, 0, 0. If we convert it, this is a binary number. Let's consider it as a binary number. If we convert it to decimal, it will be 0 in decimal. So that's why m naught is called m naught or m0. Let's take another example. For example, this guy, 1, 0, 0. Let's consider it as a binary number. So if we convert this to decimal, this will be 4. That's why this is called M4. No? 1, 0, 0 is M4. Okay. One important observation here is that the order of the variables, the literals, are very important. Is actually fixed for the definition. So we always have x, y, z. Okay. So when I said M4, I mean this is corresponding to 1, 0, 0, and I mean this one is x, this 0 is y, this 0 is z. You cannot flip the orders. You cannot say it's y, no, because this will give us basically a different subscript and also different combination. Okay. What I said for the main term is also applied to the definition of the max term. Okay. So let's express one of the max terms here. Okay. Like M capital 1, for example, this guy here. Okay. We said that the definition of the max term is that it will be 0, 0, opposite to the main term, at one particular or specific combination, and one otherwise. So let's do that for M1 here. Okay. So M1 is X or Y or Z prime. X or Y or Z prime. Okay. So let's verify this definition, that this expression X or Y or Z prime will be only 1, 0, I'm sorry, at a certain combination of X, Y, Z, and one otherwise. So let's see. Let's start by the first one, 0, 0, 0. Okay. When x is 0, then y 0, so 0 or 0 now, or 1, this will give you 1. So M1 here, so this is, let's consider, let's write M1 here. Let's write it as another color and make it here as well. So M1. Okay. Or let's take M0 better, because I am gonna express something with M0. So I wanna relate M0 to M capital 0 with M small 0. So let's do with M0 instead. Okay. Okay, for M0 is equal to X, Y, Z. X or Y or Z. Okay. So when x and y and z, all of them are zeros, then 0 or 0 or 0 or 0 plus 0 plus 0 will give you 0. And we said that any max term will be 0 only at one particular combination of x, y, z, then one otherwise. We get the 0 here from just the first combination of x, y, z. So we are expecting now other combinations will give us ones. Let's see. Then 0, 0, 1. So 0 or 0 or 1 will give us 1. Basically, whenever you see 1, just put 1 because 1 or anything will give you 1. So 0 and 1 here, so again 1. 0 and we have 2 ones actually, not only 1 1. So again 1. Then we have all 4 ones for x here. So again 1, 1, 1, 1. So look at m0 small and m capital 0. M small 0 is 1 at a particular term, is 0 otherwise. M capital 0 is 0 at a particular term, 1 otherwise. And you can do the same for M1, M2, M3, you know, for both max term and min term. Okay? And you will find the same properties like what we saw for M small 0 and M capital 0. Okay? Now, the last, piece of information or property for the max term and min term, as they are very related to each other. Just look at M small 0 and M capital 0, these two columns here. Just look at them. So let's go back to our normal color. If we look at them, when M small 0 is 1, M capital 0 is 0. It's complement, right? Then, when M small 0 is 0, which is basically the rest of the terms here, so basically M capital 0 was 1. And you will find the same for every particular combination. I mean, for every related max and min term. For example, M1 small and M capital 1 will be, you will find them like this. You will find M1 like this, 0, 1, 0, 0, 0, 0, 0, 0. And you will find M capital 1 as follows, 1, 0, 1, 1, 1, 1, 1, 1. Look again. When this is 0, this is 1. When this is 1, this is 0. And again, for these zeros, we have 1s. So we find that M0 is equal to M capital 0 complement. And we find that M1 equal to M1 complement. So in general, Mi equal to Mi complement. So any min term, its complement will be the corresponding max term. Okay. Can we prove that? Yeah, that's very simple actually. Okay. So let's take M0. So M0 is equal to X prime or X bar, Y bar, Z bar. And we are saying that M0 bar, M0 complement will give you M capital 0. So let's do that. So M0 bar equal to X bar, Y bar, Z bar, and the whole is bar. You remember, guys, De Morgan's theorem. So with De Morgan's theorem, we can say that this is equal to, so any and will be or, and any literal will be its complement. So any and will be or, so we'll have two ors because we have two ands. Then X bar will be X bar bar, Y bar bar, Z bar bar. This is equal to X bar bar is just X, Y bar bar is just Y, Z bar bar is just Z. What is this? This is M capital 0. So basically, M small bar is equal to M capital 0. Okay. So that's basically the definition of the max and the min term. So it's time now to know what is the importance of these max term and min terms. What is the importance of these new definitions that we studied now? Is basically we can express any Boolean function as sum of min terms or product of max term. And this is basically, you know, the basic or the most primitive or the canonical form to represent any Boolean function. Okay. So basically we can express any Boolean function as sum of min term or sum of product. And I will explain in a moment why min term is corresponding to product. And we can express also any Boolean function as a product of max term or product of sum. And now let's see how min term is corresponding to product or ending, and max term is corresponding to sum or ORing. Just go back here and see. It's if we take, for example, M1 as an example. M1 is x bar dot y bar dot z, ending or product. We multiply, you know, in other term, although that's not so accurate, x bar by y bar by z. And you know, as you see, all of them are just products. The opposite is the max term. For example, M0 is x or y or z, or in other term, although it's not accurate, x or sum with y or plus y plus z. Okay, so let's see how we're gonna do that. So we have here example, basically two examples. We have two functions, f1 and f2, and here is the truth table of f1 and f2, the relation to the variables x, y, and z. Okay, and we want to express both f1 and f2 as sum of product, SOP, and also product of sum, POS. Sum of product is sum of min term, product of sum is product of max term. Okay, so the basic rules that we're gonna follow here is that sum of min term, so we look at the locations of the one of the function, then we add just the corresponding min terms together. So that will be sum of min term, sum of product. Or we look at the zeros, and remember, max term will be zero at only one combination and one otherwise. Okay, so we look at the zeros and we multiply them together or add them together, then this will be a product of sum or product of max term. Okay, so let's do that for f1. So let's start by the sum of product. So let's start by f1. So let's start by the sum of product or sum of min term of its min terms. So f1 can be expressed as the sum of. Now let's locate where are the ones of f1. Here is a 1, so, and this is actually m1. Remember, this is 0, 1, 2, 3, 4, 5, 6, 7. Because again, the index, the subscript of the min term is very important. Okay, this is m1. Again, we have here a 1. This is m4, and this is m7. So f1 can be represented as the summation of m1, m4, m7, and you can write them, you know, in a more reduced form as 1, 4, 7, just like this. And we know that you mean m1, m4, m7. But where is the expression itself? That's fine, you know. You just write the corresponding value of m1, m4, m7. So m1 is, you don't need to remember them. Of course, they are written here, you know, but you don't need to remember them. Just look at the literals, the variables here. Whenever you see a 0, that's a prime or a complement. Whenever you see 1, that's the variable as it is. So M1 is X prime, Y prime, Z. X prime, Y prime, or complement Z. M4 is here, this guy. So this is X, Y prime, or Y complement, Z complement. M7, X, Y, Z. Very simple, right? And very easy also. And by the way, you know how to get a truth table from expression. That's easy. And that's what we learned so far. This is the way of how to get a function, an expression from a truth table. Okay? This is the opposite way. Now, how we express F1 as product of sum. So, F1 again as a product of sum or product of its max terms. So, F1 is product of. Now we look at the zeros, not ones. So, this is M capital 0. M3, M5, M6. So you can write this as follows: M0, M2, M3, M5, M6. And one thing here is that you just look at the sum product, the product of sum. This should be 8. So we have here 3, we have here 5. Because basically the main terms are the ones. So if you have 3 ones, then for sure the rest, which is 8 combinations, should be 5 zeros. Okay. Now where is X? And of course you can write them as follows: 0, 2, 3, 5, 6. Or now, when you write the max term 0, now you take the literal as it is. If you find 1, then you take the complement. So, for example, M0 is a max term. This should be X, Y, Z, not X prime, X or Y or Z, not X prime. So we do just the opposite of what we did with the main term. So this should be X or Y or Z. Then 2. 2 is that guy. X or Y bar, Z. X or Y bar or Z. Then 3, this one here. This is X or Y bar or Z bar. Then 5, this one. This is X bar or Y or Z bar. Then 7, all of them are bars: X bar, Y bar, Z bar. Okay. I will just now write F2. So this is basically F1, now F2 here. I will just write, sum of product first. So F2 is here, and those guys as well. So this is M3, 4, 5, 6, 7. So 3, 5, 6, 7. 3, 5, 6, 7. And you just take it as exercise to find it was expression, And as a product of sum, F2 will be, the rest. You don't need to look for in the truth table anymore. Just write down the rest of the numbers that you didn't write. So 0 is not there, 1 is not there, 2 is not there, and 4. If you wanna check 0, 1, 2, and 4. These are the max term. Okay, that's very good. Now another question, which is also insightful, because this will give you insight about, the relation, another property of, or another usage of the min and max term. In the first example, we get the function itself, the min term or the maximum, or the expressions for min term and the max term. But how about their complement? Okay, their complement. Okay, so basically here, let's write down, some insightful property for any function expressed as a sum of product or product of sum. Okay, so for f1, we find that f1 is the summation of m1 or m4 or m7, right? So f1 prime should be m1 plus m4 plus m7 prime or bar. And using De Morgan's theorem, this would be just, flip, the or to be and. So this will give you m1 prime, m2 prime, m7 prime. And what's m1 prime, m2 prime, m7 prime? This is basically the max term. So m1 capital, m2 capital, m7 capital. So f1 prime is basically, the multiplication of, or the product of 0, 2, and 7. This is 7. So look, f1 is the summation of 0, this is 4, I'm sorry, this is 4, this is 4, 0, 4, 7. f1 prime is the product of 0, 4, 7. What is the product of sum? We should guess without even analyzing it. So so this is for the sum of product. For the product of sum, f1 is the product of, that's very big, m0, m2, m3, m5, m6. So f1 prime should be, it should be m small 0 plus m small 2, m small 3, m small 5, m small plus m small 7. But we can just analyze it, I mean prove it. So just take the prime of this. That's better than making a very long bar. So f1 prime equal to m0 prime plus m2 prime plus m3 prime plus m5 prime plus m6 prime or bar. So f1 prime is equal to m small 0 plus m small 2 plus m small 3 plus m small 5 plus m small 6. That's very insightful, a very beautiful property. You get f is the sum of 0, 4, 7, f bar for sure, product of m capital 0, m capital 4, m capital 7, and so on and so forth. Okay. Can we prove that more? Yes, just write the expressions and see. So from the sum of product here, f1 is x bar y bar z plus x y bar z bar plus x y z. So f1 is, just take the product, I'm sorry, just take the complement. So this will be x plus y plus z bar, x bar plus y plus z, x bar plus y bar plus z bar. Right? What is this? This is basically, let's look here. x plus y plus z bar, x plus y plus z. This is M1. I'm sorry, this is 1, not 0. This is 1 again. Very sorry for this. Yeah. So x plus y plus z bar is in M1 capital. What is x bar plus y plus z? X bar plus, this is M4 capital. What is x bar y plus y bar plus z bar? Just look here. This is M7. Okay. I mean, once you get the sum of product or a product of sum of any function, you instantly can get its complement in a very easy way. And I will let you know F2 for you guys as exercise, F2 prime for you as exercise. Okay, so this is basically was the basic introduction for the min and max terms. Okay, which what they call canonical form, okay, because they are the basic or the most primitive way to express functions. In the next video, we're gonna go more about the benefit of using the min term or max terms in expressing functions, and the hardware benefits that we're gonna get if we do the implementation based on sum of product or a product of some form of any function. Thank you. Bye-bye.